Okay, great. Well, thank you for letting me speak today. Yes, the Oregon Department of Geology and Mineral Industry did participate in this project, and we're very grateful for that. It kept me in my chair for 3 years. We did two parts. We did the data data development, and we had 11 deliverables. And then I have in year 2 that we have a LIDAR and thermal infrared project, a sub-project, thermal gradient project. I should add a third one with DAS contracting. And the permitting part, DAS is our Department of Administrative Services. So we spent a little bit under half of our funds awarded for this part of the project. And I want to thank again DOE and Arizona. That's quite a job. So thank you. Before I start, let me kind of summarize what we did in the data development. Just kind of go around the block here on the map. I was able to, and the department was able to get 10 projects published through our publication process. We did produce an interactive web map, and you can see here part of that is displaying all the records that we were able to scan and put up. So here you see a well log, but there's also permitting records, any kind of reports, and even large-scale maps that you can view and also download. The map you see behind you is just an Esri rendition of the multitude of points that we were able to get, and they include all the various 11 data sets that were put together. So just to kind of summarize from the state geothermal website, it looks like I was able to get 25 deliverables in. Yay, some of them were on time. And about 40,000 records and 29 downloads. And we did set up services, web services here at Tagami. And for data management, that was a huge step for us. Also, putting all this information out there through our website free for anybody to use was a cultural switch for us. So those are the two big highlights as far as data management is concerned. I also would like to thank a lot of people for helping me on this. It just wasn't myself. For the TIR, thermal infrared, LIDAR, we used Watershed Sciences here, a local company, now part of the Quantum Group. And then the other agencies that helped me get that part of the project through. The thermal gradient drilling, we used Wellsco Drilling Corporation out of Nevada. Surprisingly few, if any, Oregon drilling companies were interested in doing the work. And then there was a multitude of people who were involved some way and somehow in this the drilling project. And I ought to mention here that Lori Doak and Stephanie Tu from our DAS showed me the ropes on how to go through the bidding and purchasing and proposal steps that was part of our state process. And that was my third project. And of course, all those people here from Tagami that also were contributors, and they're on the right. So we had our project was two-part. We divided up into as you can see there, thermal infrared and co-acquired LIDAR imagery. From our research, we found that we were probably the first ones to combine the two and see if just to see if they would be able to kind of reveal possible low amplitude surface anomalies. The combination of the two is useful when you're doing aquatics and looking for temperature change in water. So we decided we'd kind of see if we could do it on the surface. The drilling was going to follow, and we would select areas for imagery. We'd go in and see if they were suitable drilling targets. Timing was a problem here in the short duration, so it was kind of putting the cart in front of the horse in some cases. We did drill in areas that had that we did acquire LIDAR imagery. It wasn't necessarily the best place to drill. So you can see there the purposes and our objectives. Is it a useful tool? That's one thing we kind of looked at, and then we did a pilot study or looked at the pilot area to reveal if there is some application for finding surface anomalies, and I'll talk about that here in a minute. And then the last part of my presentation will go into the thermal gradient drilling and the parts and pieces that were involved here. As you can see, we did do the kind of the regular stuff, getting thermal gradient measurements, logging holes, collecting rock chemistry samples. We also decided to map the areas surrounding each one of these locations to drill, and usually that included a quadrangle worth of mapping. So here, this slide kind of gives you a rundown of where these 5 areas that we flew, about 274 square miles. I'm giving you a price here. It was $598 per square mile, and we did collect high resolution LiDAR with that money. And you can see it's basically covered 3 counties, and most of our work though is Lakeview in Lake County. Flying 2 separate areas, or flying areas that are far apart, was a little bit of a logistical problem. Finding water for calibration, particularly in the eastern part of the state, was also an issue. This map is an Esri eye candy thing. It's where you can swipe back and forth. The TIR thermal infrared is on top, and it's colored just to show you different temperature values. And then you can swipe over the top of the LiDAR, underlying LiDAR. So here was our pilot study area. It's the #1 block. It's in Lake County. We call it the Summer Lake area, and this is the northern part of the Summer Lake Valley. I've got 2 things here that I'll talk about briefly. Is that we've got the specifications, and then I'll talk a little bit about what the colors mean and what you see here on the map. Well, starting with specifications, I think one of the hardest or the tightest specifications, or the one that could have caused the most problems but didn't, is that we had to fly at night between 2 a.m. and 6 a.m. That was the coldest part of the night. We needed to fly during the coldest part of the year, and that was through the records from January through March. There couldn't be any snow cover on the ground. Of course, the winds couldn't buffet the plane around, and there could be no visibility problems. You know what? Out of all, we had 4 flight times, and we didn't have any problems. So we were lucky. Now you're seeing this map here. It shows you the adjusted radiant temperature in relation to water, and the white area there, as you see, is Anna Lake, and that body of water is warmer and than the surrounding ground. The air temperature is about halfway in the middle of here of the high and the low that you see on the scale. The red areas, the colored areas, represent warmer relative to the darker black areas, which are colder. If you look, these bluffs here, the south-facing and the east-facing bluffs, apparently are due to the heat storage capacity of the basalts and have nothing to do with any kind of anomalies. That was kind of a surprise for us a little bit. If I had more time, could show more pictures, I'd show you the individual juniper trees and everything else that you're able to look at. I should mention that the base here is a slope shade LiDAR base, and the TIR imager right now is draped over the top of it and with a transparency applied to it. In order for us to kind of look at whether there's a low amplitude thermal anomaly, we needed to unmask the vegetation and certainly take the water off, and we did that through a number of GIS exercises. The TIR mask creations are listed there on top of your top of your screen, and we went through 1, 2 water mask iterations, and you can see the iterations to remove the vegetation from juniper trees all the way down to grass. What it shows here on the map is that the gray areas are the mask areas, the black through the purples and the fuchsia are the apparent temperatures that are left over. You can see that we are starting to look at possibly some anomalies here, down in through here, and so that was encouraging. We also, using LiDAR, can see all sorts of structure in this. These are all sand dunes, by the way, and we can start to see these Holocene faults coming through here. I've got 3 shown here, but I bet you there's a dozen here if we really wanted to do a real hard analysis on it. We drilled the well here, SL1, right here in this gravel pit, and it is, actually there is an anomaly next to it on the surface, and it was dry here, I should add. So that's basically what we did to process the TIR and the LiDAR to look for these anomalies. I ought to mention too that we did hit in the shallow advective zone, probably about 80 meters down, around 24 degrees C, and I'll talk about that when I get to the drilling. So, how was it? How effective are they? Well, there's no doubt that LiDAR can be used to find structure. In fact, ORMAT used LiDAR and geologic mapping for their work that they're going to do to about 100 miles to the northeast at Glass Buttes. It's indispensable for mapping, geologic mapping. We tend to map in those areas that we have LiDAR right now. And granted, those both are for any purposes, and particularly geothermal exploration would be ideal. Now, were we able to really recognize low amplitude anomalies? I guess the answer is maybe. We did see some differences. We don't know if they're necessarily geothermal. Time and money did not allow us to go back in and do any kind of soil probe or any other kind of work to really firm that up. And certainly when you're talking about emissivity with temperature work, there's a lot of variables that need to be sorted out. But one thing you can do, and I think what it does do very well, is shows you near surface or surface groundwater or seeps. Right now you can see that using this LiDAR and the TIR, we found a lot of different seeps, cold and warm water. They're basically the 2 warm water spring areas that's shown on the map are here at Buckhorn and down here at Lost Cabin, and the rest of these are what we could determine from our pilot work. So kind of switching the gears to the geothermal gradient wells. Again, Wellsco is our driller. It took 5 phases to really get this project going, and from the site development, or site selection, and the proposal, and then all the permitting, the bidding, actual drilling the well, and the plugging and abandonment of the wells was the easiest part. We had a criteria to look to site the wells. Again, it was in the Oregon's Great Basin Range area. It's on public lands. We didn't want to go after public, and then we kind of limited that to shying away from BLM. Forest Service was the next that we looked at, and finally we settled on only state lands where I could actually turn a permit around in 3 months. We looked at areas lacking geothermal information. We looked at areas that had geothermal potential, and we wanted to be next to transmission lines, because there isn't going to be any more new transmission lines in Oregon. I hesitate to say that's probably everywhere in the Pacific Northwest or the western part of the United States. There's areas that we excluded too, active and inactive leases, where the data development and our ability to get all of the permits and geothermal well permits online and into our geothermal information system, so we didn't go in areas that were previously prospected. And we shied away from that, from our sage grouse issue, and that pretty much eliminated all but 3 sites. So there you go. That's what we've got. And I ought to mention wilderness. So those are the 3 sites we settled on. And you can see with our spud dates, we started in April, and we ended drilling a little bit in the first 2 weeks of May in the last hole. We did, our data collection was, the typical cuttings. We did each of the well logs for each well. We did selected rock chemistry intervals for only 2 of the wells. The one well that we didn't, the Oregon Military Department well, was all in sediments. There was no volcanics. The thermal gradient logs, the USGS did that kindly for us. They ran 2 runs. the run you see here is the first run in June, and it actually is took 30 days for our wells to equilibrate. What you're looking at there where the advective zones are marked, the black line that you see here is for the Summer Lake well, and that sharp reversal is not due to an instrument failure. The second run showed the exact same pattern, same line. What I think we hit there, we lost is the boundary between the overlying Miocene volcanic rocks and the underlying Oligocene volcanics, and this is a zone of high permeability porosity, and we lost the well here and just about had to abandon this one. We actually pulled the tubing out of this well to the tubing out of this well to see if we could save it. So it's pretty tough. We also hit another advective zone out here in Mount Hare County at our Baker Pass. That's the Folly Farm well, and it also shows an advective zone, a little bit higher temperature, about 26 degrees C. The 30 to 45 degrees C per kilometer thermal gradient is for the Oregon, the Christmas Valley well, and it's pretty typical of what I think a sedimentary well gradient looks like. The well designs, as you can see, we drilled 1,000 feet. We didn't get 1,000. We only got to 960 at the Summer Lake well. That's called the Pitcher Gore Down SL1. We just put minimal amount of casing to the first water, and then we drilled rotary mud all the way down. And in each one of these holes, we had our sets of problems. Each one of them had no flow zones. We lost all sorts of circulation. It was not an easy drilling at all. So the other part of our objective was the geologic characterization around of the areas surrounding each of the thermal gradient wells. And these are three maps of the three locations of drilling. Each one of these maps is in one geology. The days that we spent on the field were minimal. I think we had 30 days to do all these. So these, they could be a lot more refined. I'll just say that for the record. As you can see, we drilled in sites that were previously disturbed, so I could get my NEPA permitting out of the way, satisfy my cultural stuff, so that wasn't a problem. I had to get permits for all three of these sites from the state. It wasn't too much of trouble. This site happens to be the former site of a backscatter radar system, a Cold War era of installation, and so you can see the antenna here array. The geologic, I guess, criteria for looking here, particularly here in the Baker County, or I'm sorry, in the Mount Hare County Baker Pass area, was the intersections of the Steens Mountain fault zone. There's two segments, the Man Lake up here and the Crowley, Man Lake to the south, the Crowley section to the north, and then the intervening faulting that is part of the extensional faulting in between. And we were hoping we would get some more water there, and it proved true. So one of our exploration models was born out here. The criteria for drilling here was, of course, the these north-northwest trending faults. There's, as you recall, the actual pilot study area is just to the south of here, and we're right there at the drill site. And so we have Holocene faulting here. We have also geothermal fissures that we were keying on. This drilling right here was really out there where there had not been any data previously. It's flanked by these northwest faults, probably Pleistocene and Pliocene faulting. There's also Pliocene Mar volcanoes out here. So we thought this area had a particularly interesting set of geologic circumstances to look at. So as far as our days of management goes, I just wanted to briefly show you one thing that we really wrestled with here is that how do we get the LiDAR and the TIR information out to the public when we're talking over 500 gigs worth of data, and that includes the last data. Ordinarily, DGAMI or our agency would not let this information go without some kind of charge. And in fact, we do have a handling fee charge just so that somebody spends a day to download this and get it mailed out again. Otherwise, it's all free. If you come in here and want to, come in and actually physically sit down and load it here, we'll let you do that. So that's been our biggest issue to date, is to get the real this huge data set out, plus the fact that we're giving it away free. That's been the DGAMI's big issue. So that's all I've got to say. Thank you. Any questions?